Okay, after we got the internal shear force V, then we have to draw the internal shear, internal bending moment M. Okay, so the M, the unit is kilonewton meter. Okay, and then we draw the X in meter. Alright, so what is the equation for M? Okay, previously I forgot to wrote 2, power of 2 here, so is M1 equals to 9.33 x1 minus 3 x1 squared. Alright, so the segment is x1 equals 0 to x1 equals 2, and from 2 to 3, right? So what happened here in x1 from x equals to 0 to 2? So you just put the value here, x1 0, so the M will be 0, isn't it? And when x1 equals to 2, because this is the borderline, 9.33 times 2 minus 3 times 2 squared, so the value is 6.67. So you got 6.67 positive. So what happened in between this x is 0 to 2? How do we draw it? Is it straight line or curve or whatever? So actually, if you understand it, if you understand this parabolic equation, you can do it straight away. That actually this is a curve, a parabolic curve, isn't it? And this is the x squared, and the a here, the coefficient is minus, so which means that the graph is sad, not smile. Okay, you got what I mean. Okay, but that's another thing we learned in 6.2 graphical method. What is the relation between slope of M with the V? Alright? Okay, previously there was no 1.56 here. Okay, so what's the relation between slope of M and V? We know that actually the slope of M is actually the value of V itself. That's what we learned in graphical method, right? And then the slope of V is the value of the variation of the load, the W, the distributed load. Okay? So, what happened here? How do we interpret this region, x equal to 0, x equal to 2, from this value to that value? So, okay, because we have these two values, I mean this line, so let's find this intersection point. Okay, go back to V1 for the equation. To find this intersection point, you have to put V1 equals to 0, isn't it? V1 equals to 0, and then try to find x1, which is 9.333 divided by 6. So you got 1.56. So this intersection point is 1.56 meter, somewhere here, 1.56 meter, right? So what happened is the graph, the graph between 0 to 2 for M will be like this. Okay, and the maximum point will be here. Okay, let's make it correct. Oh, okay, because 2 is here, so that's why it's 2 more. 2 is here. Alright? How do we know the shape is like this? Again, you can plot one by one. You can have, for instance, x equal to 0 0.1, 0 0.2, 0 0.3, blah 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 blah, 1, 1.2, 1 until 2. You can do that. But that's a waste of time. If you understand the V value, relation of the value with the slope of M, so we can do it straight away. So what happened here? Can you see that actually the V value is changing from positive 9.33, it decreases until 0 here, isn't it? At x equal to 1.56. And then it becomes negative until the value becomes minus 2.67 kilonewton at the location of 2 meter. So what does it mean for this M? So what happened is that the slope of M between 0 to 1.56 here, 1.56 will be positive, right? The slopes will be positive. See, positive slopes. Positive slope, for instance, this positive slope, isn't it? This is slope equals to 0, and this is the maximum slope of 9.33. All right. That's why we say that the slope of M is the value of V itself. All right. And then after 1.56 until 2, what happened? The slope becomes negative, and it reaches this point, which is the slope here. The slope here is actually minus 2.67. Right? So that's why we don't need the more points. We just have to interpret the slope here corresponding to the V. Right? And then what happened between 2 and 3? So for 2 and 3, we go to M2. M2 equals to 6.67 x2. But bear in mind, for x2, we define that the range from 0 to 1, but it's from right to left, not left to right. Right? Not x equals to 0 here, 1 here. No. It's x2 equals to 0 here, and x2 equals to 1 here. Right? So if you put x2 equals to 0, it becomes 0. It means, where is the 0? Not here, it is here. Because remember, x2 starts from the right. Right? And then if you put x2 equals to 1, so you will end up at 6.67, the same point. The direction is the straight line. How do we know this is straight line? First, you can look at the equation of M2. M2 equals to 6.67 x2. Obviously, it's a straight line, isn't it? x2 power of 1. Then the thing is, again, the slope of this will be this, isn't it? 6.67. So this slope will be 6.6. Sorry, minus 6.67. Minus 6.67. This slope. Alright? So this is your shear force diagram. This is your bending moment diagram. Alright? So let's go back to the shear force diagram for a while. Okay? Let's interpret that. Can you see that actually here, in this region, between x1 equals to 0 to x1 equals to 2, the shear force diagram has this slope, isn't it? The negative slope. If you calculate this, if you try to find this slope, definitely the value will be 6. Minus 6, sorry, minus 6, because it's downwards. 6 kilonewton per meter is downwards, okay? Minus 6. And can you see that the slope here, between 2 and 3 here, is 0. Why? Because if you look at the diagram, the beam itself, there is no distributed load. Okay, that's why we say, that's why in 6.2 we learned that the slope of shear force diagram is actually the value of the distributed load. That's why distributed load here minus 6, this slope is minus 6. Distributed load here, there is no distributed load, so it will be 0. Alright? Okay?